Module 4, Lecture B, Reports and Audits. By the end of this lecture, you will be able to format medical summaries into readable tables and narrative text using built-in string tools, sort and filter records to highlight clinically relevant patterns or audit exceptions, and apply simple de-identification strategies to example datasets before reporting. Readable medical summaries. Formatted tables turn raw medical values and codes into clear summaries that clinicians can read quickly. Consistent columns, spacing, and text cleanup make information easier to compare and help reveal missing details. The goal is not just a neat layout, but better recognition of key facts in patient summaries and audit reports. Consistent formatting makes medical summary tables easier and safer to read. Dates, units, labels, capitalization, and placeholders should be standardized so values are clear and comparable. String tools can clean extra spaces and normalize text, helping tables look professional and reducing the risk of misinterpretation. Formatted tables help different readers quickly find what matters most, such as abnormal results, overdue reviews, or missing documentation. String-based formatting can create clear headings, align categories, and combine related fields so summaries are easier to compare and read. These tables do not replace clinical judgment, but they make patterns and priorities easier to recognize for better decision-making. Python code. Formatted tables. Create readable clinical tables by formatting rows clearly, using built-in string methods to control alignment. Always de-identify patient information to protect privacy. We create a small audit dataset where each patient visit is stored as a tuple. Each record includes the patient's name, visit date, blood pressure readings, visit setting, and planned action. This structure makes the data easy to organize, format into tables, and review for high-risk cases. The make code function creates a privacy-friendly patient identifier from a patient's name and row number. It trims the name, takes the first letter of each name part as uppercase initials, and combines them with the row number formatted as 2 digits. The result is a de-identified label that stays unique within the dataset. The table is set up by defining column headers such as ID, date, blood pressure, setting, and action, each with a fixed width for consistent alignment. The header row is built by left-aligning each label and separating the columns with vertical bars. A matching dash separator is then added beneath the headers to clearly separate them from the data rows and improve readability. The process builds a formatted table by creating one row for each record. For every entry, it generates a de-identified patient ID, formats the blood pressure, cleans and capitalizes the setting in action, and combines these values with the date. Each field is aligned to the required column width, then joined with vertical bars and added to the list of rows. The code prints a clear blood pressure follow-up report by first showing a title, then aligned column headers, and then a dashed separator. It loops through the prepared rows and prints each one, presenting de-identified patient details in a compact, structured format. The code filters blood pressure records to find cases that may need attention, using thresholds of 140 for systolic pressure or 90 for diastolic pressure. It then counts those high-risk records, creates a short summary of how many need follow-up, and prints the result for the user. This script turns a small set of patient records into a readable, de-identified audit table. It replaces names with unique patient IDs, shows key details such as date, blood pressure, setting, and action, then flags records needing follow-up. High blood pressure is defined as a systolic reading of 140 or higher, or a diastolic reading of 90 or higher. The script ends with a brief count of how many records require follow-up. Readable rows. Readable rows make medical summaries easier to scan and reduce confusion. By using built-in string tools to control spacing, capitalization, and alignment, raw records can be turned into consistent text. A predictable row format helps clinicians quickly find key details such as dates, locations, measurements, outcomes, high readings, or missing documentation. Clear row formatting makes medical summaries easier to read and less prone to misunderstanding. Use consistent capitalization, standard date and time formats, clean spacing, and numeric values paired with units. Simple labels, separators, and built-in text functions can help standardize information so it matches what readers expect. Readable rows should balance enough detail with brevity so the reader is informed without being overwhelmed or misled. Choose only relevant information, organize it logically, and use string tools to fill gaps and standardize entries. This turns tables from raw data dumps into clearer, more professional reports that support accurate interpretation. Python code. Readable rows. Use built-in string formatting to present clinical rows clearly, so reports stay easy to scan during review. Before sharing any summaries, remove or mask identifying information to protect privacy. A small set of patient audit records is created for testing and demonstration. Each record stores an identifier, date, ward, blood pressure, and follow-up status. The examples include inconsistent ward formatting, a pending review, and one record with missing blood pressure and documentation notes. The mask identifier function turns a raw identifier into a safer report label. It keeps only the last two characters for limited reference, then adds them to the word patient. This helps anonymize the original identifier while still leaving a small clue for recognition. The format ward function standardizes hospital ward names by first removing extra spaces from the beginning and end of the input. It then converts the cleaned name to title case, so each word starts with a capital letter. The result is a consistent, easy-to-read ward name across records. The make row function creates a compact, readable line for a medical record. It anonymizes the patient identifier, standardizes the ward name, uses not recorded when blood pressure is missing, and capitalizes the record status. It then combines the date, ward, patient label, blood pressure, and status into an aligned table-style string. The code creates a clear, readable table for a medical summary. It first prints a title, then adds column labels for the date, ward, patient, measurement, and outcome. A dashed separator follows, making the upcoming data rows easier to read and understand. The code goes through each medical record, formats it into a clear row, and prints the result. During formatting, it masks patient identifiers and standardizes ward names to protect privacy and improve readability. This makes the summaries easy to review while keeping confidential information secure. The code audits the records for missing blood pressure information by counting entries where the blood pressure field is empty. It then creates and prints a short summary showing how many records need follow-up for incomplete documentation. The script turns medical records into a clear, consistent summary while protecting patient privacy. It masks patient identifiers, standardizes ward names, and marks missing blood pressure values as not recorded. Each record is shown with the date, ward, patient label, blood pressure, and status, followed by a count of records missing blood pressure documentation. Narrative summaries. Narrative summaries turn structured medical data into clear sentences that are easier for clinicians and administrators to understand. They connect raw fields such as diagnoses, dates, and measurements into a concise story of a patient's case. By formatting details consistently, these summaries make reports clearer and support faster, more accurate decision-making. A strong narrative medical summary includes only the fields most relevant to its purpose, such as admission details, follow-up plans, test results, or screenings. Built-in string tools help make these summaries consistent and readable by cleaning extra spaces, standardizing labels, and adding default text for missing information. This reduces formatting-related confusion and helps reports sound clear and professional. Narrative summaries should be shaped by their audience and purpose, such as clinical handover or audit. The same patient data may need different emphasis, depending on whether the focus is delays, missed observations, or documentation gaps. Summaries must stay within the evidence, clearly noting unknown information, rather than making assumptions. Effective healthcare summaries are concise, consistent, and easy to understand. Python code. Narrative summaries. Create concise summaries from structured records by cleaning text before turning it into report sentences. Before sharing or printing summaries, de-identify any examples to protect sensitive information. A small list of patient records is created for teaching purposes. Each record is a simple dictionary containing basic information such as a unique patient identifier, an initial, and an age. The text shows how strings and integers can be stored together in structured records. This patient record stores key visit details for a later narrative summary. It includes a diagnosis of pneumonia that will be cleaned for consistent formatting, a 3-day hospital stay, a blood pressure reading of 138/82, and confirmation that a follow-up appointment was arranged. The code creates one patient record as a dictionary within a list used for narrative summaries. It stores the patient identifier MRN 99217, the initial B, age 54, and the diagnosis being reviewed, diabetes review. This patient record stores key visit details used to create a medical summary. It shows that the patient did not stay overnight, records a blood pressure reading of 151/94, and has no follow-up appointment listed. The record is one item in a larger list of patient visits. The clean condition function standardizes medical condition text so it appears consistent in summaries. It removes extra spaces, converts the diagnosis to lowercase, and then capitalizes the first letter for readability. This simple cleanup helps produce clear, professional, and uniform condition descriptions. The follow-up phrase function standardizes follow-up information by trimming spaces and converting the input text to lowercase. If the result is yes, it returns a phrase saying a follow-up was arranged. Otherwise, it reports that no follow-up was recorded, helping keep the output consistent despite minor formatting differences. The anonymize function de-identifies patient records by changing a record number into a safer identifier. It takes the last 2 characters of the original string and adds the word patient before them. This keeps records distinguishable in the dataset while helping protect patient confidentiality. The function prepares a patient record for a clear summary by anonymizing the patient identifier, standardizing the diagnosis text, and converting the follow-up status into a readable phrase. Together, these steps produce clean, consistent details that can be used to build a concise narrative for each patient. The function builds and returns a formatted sentence summarizing a patient review. It includes the anonymized patient identifier, age, medical condition, latest blood pressure reading, length of hospital stay, and whether follow-up was arranged. The program prints a title for narrative medical summaries, then goes through each patient record. For every record, it uses the summary function to create a short, de-identified sentence with key details such as age, diagnosis, blood pressure, hospital stay length, and follow-up status. Each summary is printed clearly, giving a concise overview of the patient visit. This script turns medical records into short narrative summaries. It cleans and formats patient details, anonymizes identifiers, and clearly states key information such as age, diagnosis, blood pressure, hospital stay length, and follow-up status. When run, it prints concise summaries that give a quick overview of each patient's medical review. Sorting clinical records. Sorting patient records. Sorting patient records turns raw clinical data into a clearer, more useful view. Instead of keeping records only in the order they arrive, sorting by details such as appointment date, risk score, test results, or missed visits can reveal patterns and help prioritize care. In short, sorting makes important clinical information easier to understand and act on. Choose a sort order that matches the clinical purpose of the report. Ascending order shows smaller or earlier values first, while descending order brings larger or later values to the top. You can combine sorts, such as grouping patients by ward, then discharge date, then readmission risk, to create a view that reflects clinical priorities like location, time, severity, and responsibility. Sorting clinical records is not just a technical task. It also affects data quality and interpretation. Dates must be consistent. Numeric results should be sorted as numbers. And missing values need attention because they may signal incomplete or delayed documentation. Names and identifiers should be used carefully, since they may not support clinical priorities and can raise privacy concerns. Choose sorting fields thoughtfully to support accurate, fair decision-making. Python code. Sorting patient records. Sort records to make clinical priorities clear. Keep examples small so reports stay readable, and use de-identified labels to protect patient privacy. We create a small set of clinical records, where each patient record stores an identifier, assigned ward, days admitted, and risk score. Organizing the data this way makes it easier to manage and sort patients by factors like length of stay or risk level, helping prioritize clinical tasks and support efficient care. This snippet adds 3 patient records to a larger clinical dataset. Each record includes a patient identifier, ward, length of stay, and risk score, such as patients in wards A and B, with stays ranging from 3 to 12 days. The dataset can then be used to sort and analyze patients by factors like admission duration and risk level. The example keeps the demo dataset small by checking that it has no more than 6 records. If the limit is exceeded, it raises an error. This keeps the demonstration simple and easy to read. The patient records are sorted by hospital stay length using the sorted function. A lambda key selects each record's days value, and reverse order puts the longest stays first. This makes it easier to identify patients who may need review because they have been admitted the longest. The patient records are sorted first by ward and then by risk level. A sorting key uses each record's ward along with the negative risk value. so higher-risk patients appear first within each ward. This organization helps prioritize patients who may need more urgent attention. Patient records are filtered to find possible audit exceptions. Any record with a stay of 7 days or more, or a risk score of 8 or higher, is added to an exceptions list. This narrows attention to cases that may need further review because of longer stays or higher risk. The output begins with a header explaining that the longest patient stays are shown in a de-identified way. It then takes the first 3 records from the admissions sorted by length of stay and prints a brief summary for each one, including the patient label, ward, and number of days stayed, without exposing sensitive information. The output begins with a header showing that patients are ordered by ward with the highest risk first. It then displays the first 3 sorted records, including each patient's ward, label, and risk score. This provides a quick view of the highest risk patients in each ward to help prioritize clinical attention. Create a short summary that reports how many patient records need further review. The number comes from counting the flagged exceptions, which represent records with long stays or high risk. Printing this summary gives a quick view of how many cases require attention. This script reviews de-identified patient records to help prioritize clinical follow-up. It ranks patients by longest hospital stay, then by ward with higher risk scores first. It also flags records for review when a stay is at least 7 days or the risk score is 8 or higher. The output summarizes the top 3 longest stays, the top 3 ward and risk matches, and the total number of flagged records. Audit exceptions. In healthcare audits, an exception is a record that does not match expected standards or patterns and needs further review. It may not mean an error occurred, only that the record lacks evidence of an expected action, such as a test or follow-up. Sorting records by factors like date or risk score helps identify these cases and turn large amounts of data into a focused summary for safer, more systematic review. Audit exceptions help identify records that may need attention, such as missing medication reconciliation, overdue cancer screening, or unvaccinated patients. Sorting data by relevant fields like time, status, age, or due date can make these cases easier to find. However, context is essential because an apparent exception may reflect a normal patient-specific situation or a documentation gap. The purpose is to guide follow-up, not assign blame. Audit reports should make the sorting logic clear so readers understand why certain exceptions are highlighted. Urgent items should be prioritized only when urgency is well-defined, such as by severity or length of delay. Effective reporting combines technical accuracy with professional judgment, focusing on exceptions that are relevant, actionable, and useful for improving care quality and patient safety. Python code, audit exceptions. Sort records to make audit exceptions easier to find while using small examples to protect patient privacy. Built-in tools help keep the review process clear and transparent. A list of dictionaries is used to store de-identified clinical records in a structured way. Each record includes a patient ID, ward, days since admission, and whether medicines have been reconciled. This format makes it easier to manage and audit key patient information while protecting privacy. The snippet adds 3 patient records, each showing the ward, days since admission, and whether medication reconciliation is complete. One patient in Ward C is reconciled, while patients in Wards A and B are not. This dataset supports finding and sorting audit exceptions based on reconciliation status and time since admission. Set the target day threshold to 2 days to define when unreconciled patient medicines should be flagged. This creates a clear audit rule for finding records where medicine reconciliation is overdue, so only records that exceed the time limit are highlighted for review. We create a filtered set of audit exceptions by keeping only records that meet two criteria. The patient has been admitted for more than 2 days, and the record has not been reconciled. These filtered records are the ones that require further review under the audit standards. The records are sorted by their number of overdue days, with the largest values first. This is done by using a sorting key that reads the day's value from each record and reversing the order. As a result, the most overdue exceptions appear at the top, making the most urgent cases easier to review first. The code prints a clear header for a medicines reconciliation audit table. It identifies exceptions as patients whose medicines have not been reconciled after more than 2 days, then labels the key columns, patient ID, ward, and days since admission. The sorted exception records are processed one at a time, and each is turned into a neatly aligned row showing the patient ID, ward, and days since admission. The formatting keeps the columns consistent, so the audit output is easy to read. Each formatted row is then printed to display the exception details. The code prints a brief summary showing how many patient records need review. It builds the message by inserting the count of sorted exception records, giving users a quick view of the audit workload. This script reviews de-identified clinical records to find patients who have been admitted for more than 2 days without medicine reconciliation. It sorts these overdue cases, so the longest delays appear first, then reports the patient ID, ward, and days since admission. It also gives a total count of records needing review, helping staff prioritize follow-up and address potential care gaps. Filtering audit exceptions. Filtering audit exceptions helps identify clinical records that may need review without assuming they are wrong. It focuses attention on unusual patterns, such as missing follow-up dates or incomplete prescription details, while reducing the amount of data clinicians must examine. These exceptions still require professional judgment, because a gap such as a missing blood pressure reading may have a valid clinical reason. The aim is to manage data efficiently while preserving the context needed for safe, informed decisions. An effective audit filter starts with a clear definition of the exception you want to find. Broad concerns should be turned into specific, repeatable conditions, often using details such as diagnosis, date, department, and relevant exclusions. The filter should be broad enough to catch possible problems, but focused enough to avoid sending reviewers too many irrelevant records. When filtering audit exceptions, present the results with clear context so unusual records are not mistaken for confirmed problems. Describe them as cases needing review, and organize them in ways that support action, such as by urgency or service area. Handle the process confidentially and fairly, with the goal of improving data quality and patient safety, rather than assigning blame. Python code, filtering audit exceptions. When reviewing clinical records, focus on filtering audit exceptions, prioritizing cases by clinical urgency, and removing identifying information before reporting findings. We create a small dataset of clinic audit records, where each record stores a patient's name, clinic, days since their last HbA1c test, and known allergies. This gives us structured sample data that can be used to filter records and identify audit exceptions. The audit begins by setting 2 adjustable rules. One defines a 180-day limit for how long a patient's HbA1c test can go before review, and the other marks records with missing allergy information. Together, these settings make the audit criteria clear and easy to change. The process builds a list of diabetes clinic records that need review. A record is added when it is overdue for the blood sugar test review or when its allergy note is missing. This filters the full record list down to the key exceptions that require follow-up. The code sorts audit exception records, so the most overdue items appear first. It orders them by the number of days since the HbA1c check, using 0 when that value is missing. This prioritizes records with the highest overdue count. The audit report begins with a brief header and column labels for the patient ID, clinic name, HbA1c days, and allergy note. It then reviews each exception record, assigns a consistent numbered patient ID, and marks any blank allergy entry as missing. Each record is printed in an aligned format, so the report is easy to read. The code reports how many records were flagged for audit review by counting the items in the exceptions list. This gives a quick summary of the review results without drawing conclusions about the underlying data. This script reviews clinical audit records to find diabetes patients who need follow-up, either because their HbA1c test is more than 180 days overdue or their allergy information is missing. It collects these exceptions, sorts them so the most overdue cases appear first, and produces a de-identified report with the key details for each case. It also gives a total count of records requiring review, providing a concise summary of the audit findings. De-identification. Remove patient identifiers. Preparing health data for analysis begins by removing patient identifiers, such as names, record numbers, and contact details. Pause. These details are needed for care, but not for studying patterns across groups. Pause. Analysts should keep only the information needed to answer the question, such as wait times, diagnoses, or medications, while protecting individual identities. Review each dataset field to decide whether it is needed for the report and whether it could identify someone. Remove direct identifiers such as names or patient numbers, unless they are truly necessary. Also check notes and comments for indirect identifiers, since specific details can reveal a person's identity even without a name. Use more general wording in summaries to protect privacy while keeping the report useful. De-identifying health data is more than simply removing names, because indirect details can still reveal who someone is when combined. Safe de-identification removes direct identifiers, reviews remaining information for disclosure risks, and protects any linking keys needed for follow-up. The aim is to keep people's information confidential, while still allowing the data to support service improvement. Python code. Remove patient identifiers. Before reporting, remove direct identifiers and keep only the fields needed for the summary. Also review any narrative text carefully to make sure it does not contain hidden identifiers. We create a small sample dataset that represents clinic records, with each patient stored as a dictionary of details. One example includes direct identifiers such as a patient's name, medical record number, phone number, and email address, along with non-identifying visit information like clinic location, wait time, and a comment. This dataset is used to show how sensitive patient information can be identified and removed. The patient records shown include personal identifiers and basic visit details. Maria Khan's entry includes her email, cardiology clinic, wait time, and a note requesting results by email. The next entry begins for James Liu, with identifiers such as his name, medical record number, and phone number. These details are part of a larger example focused on removing identifiers to protect privacy while keeping useful reporting information. This record includes James Liu's email, his association with the respiratory department, and a wait time of 46 minutes. It also contains a comment noting a request for a side room by the mayor's son, which may need redaction because it could reveal private information. A list of patient identifier fields is defined to track columns that directly identify individuals, such as names, medical record numbers, phone numbers, and emails. This makes it easy to remove or manage sensitive information, so these identifiers are left out of reports and summaries. The code sets up a group of report fields for an audit report, including clinic, wait time in minutes, and comments. These fields are useful for reporting while avoiding direct patient identifiers. The process builds a de-identified version of the records by copying only the fields needed for reporting. For each original record, it creates a safe record containing just those approved fields, then adds it to the new list. This keeps the reporting data useful while excluding direct identifiers. To protect privacy, the process replaces a specific, potentially identifying phrase in each record's comments with a safer, more general phrase. It goes through the de-identified records, checks the comment field, and uses a text replacement method to make the substitution. This keeps the needed meaning while removing sensitive narrative details. The process first reviews the original dataset fields, then shows which direct identifiers, such as names and emails, were removed. It then lists the remaining reporting fields and displays each de-identified record. This verifies that sensitive information has been excluded, while the data needed for the audit report is still available. The code checks whether de-identified records still contain any direct identifiers. It compares the fields in a de-identified record with the known identifier fields, counts any matches, and prints that number. This confirms whether the de-identification process successfully removed direct identifiers. This script de-identifies a small set of clinic records for reporting. It removes direct patient identifiers such as names, emails, and phone numbers, while keeping only clinic, wait time, and sanitized comments for audit use. It also replaces sensitive details in the comments with more general wording. The final result is a compact report that lists what was removed, what was retained, and confirms that no direct identifiers remain. Safe data masking. Safe data masking protects privacy by replacing sensitive details with broader, less identifying information, while keeping the data useful for analysis. In healthcare, details like exact birth dates or precise postcodes can reveal identities, so they should be generalized into age ranges or wider geographic areas. The aim is to reduce re-identification risk without losing the dataset's analytical value. Effective data masking starts by focusing on what the report needs to answer. Use broader groupings, such as time periods or age bands, when exact details are not required, especially in small populations. Also, review free text carefully because it can contain hidden identifiers. The aim is to keep enough structured and narrative data to answer clinical questions while removing unnecessary personal information. Data masking must do more than make records look anonymous. It must prevent re-identification from hidden clues. Initials, partial record numbers, rare events, or small groups can still reveal someone when combined with background knowledge. Safer masking uses non-identifying labels or random identifiers protected by a secure key. The main principle is to keep only the detail needed for analysis and remove anything unnecessary for the report's purpose. Python code, safe data masking. Before sharing reports, demonstrate how to mask identifying information while keeping useful clinical summary patterns. Remove unnecessary personal details so the report remains informative without exposing sensitive data. The script starts by importing pandas, a Python library for working with tabular data. This gives the code access to data frames and tools for organizing, filtering, grouping, and transforming datasets efficiently. We create a small teaching dataset that represents patient records. Each record includes a patient's name, medical record number, and age. This simple example simulates sensitive healthcare data and sets up a later demonstration of data masking. Each record is enriched with limited location and timing details while protecting privacy. The 3 records receive postcodes to indicate general areas, and the first record also gets a visit date of February 3, 2026, to provide temporal context. The dataset is updated by adding visit dates for the second and third records, set to February 6 and February 20, 2026. Notes are also added. The first confirms a completed vaccination review, while the second records that the person lives beside a named rural school. That second note may include identifiable information to be handled later during masking. The process replaces sensitive details in the third record with a generic note that a medication review was completed. The records are then organized into a pandas data frame for easier analysis. An assertion confirms that the data frame has exactly 3 entries, helping verify that no records are missing. The age band function groups a person's age into one of 3 broad categories: 18 to 24, 25 to 64, or 65 and above. This simplifies exact ages into wider ranges, which helps anonymize data and lowers the chance of identifying individuals. The postcode area function takes a postcode, separates it at spaces, and returns the first part. This keeps only the broader area or district code, which helps anonymize location data by removing the full postcode. The safe note function sanitizes text by looking for words that could signal identifying information, specifically named or school. If it finds either word, it replaces the note with a generic message saying a potential identifier was removed. Otherwise, it returns the original text unchanged. The data is anonymized by creating a new version of the data frame with privacy-preserving fields. Each patient is given a unique study ID instead of using real identity details. Ages are grouped into broad age bands, and postcodes are reduced to their district area. This keeps useful demographic and geographic information while limiting the risk of identifying individuals. The data processing reduces visit dates to month and year, making the timing less specific while keeping useful monthly information. These monthly values are stored in the masked data in a readable form. The notes are also checked and replaced when needed to remove sensitive details, helping protect privacy while preserving useful insights. The code prints a masked audit report to emphasize privacy. It displays the masked data frame in a clean format without row indices, then confirms that original names and medical record numbers are excluded from the report. This script shows how to protect patient privacy before sharing a report. It replaces direct identifiers with study IDs, groups ages into bands, reduces postcodes to broader areas, shows visit dates only by month and year, and substitutes sensitive notes with a generic message. The final masked report keeps useful summary information while excluding names, medical record numbers, and other identifying details. Limited Data reporting. When reporting data, include only the information needed to answer the report's specific question. Extra details, especially in clinical reports, can increase the risk of identifying individuals. Start with the question. Choose only relevant fields such as broad age groups, location, or time period when appropriate, and keep the report focused while protecting privacy. Limited data reporting helps protect privacy when details could identify someone indirectly, especially when combined, such as age with a rare diagnosis or location. Reports reduce this risk by using broader categories, like age bands or group locations, instead of specific dates or unusual conditions. This keeps the information useful while making it harder to identify individual patients. When preparing a report, include only details that are truly needed and generalize information when necessary to protect privacy. Unique findings in small areas can reveal identities, so use broader categories or combine data where appropriate. The goal is to keep the report useful for decision-making while safeguarding confidentiality. Python code, limited data reporting. For a clinical audit, use limited reporting by including only the fields needed to create summary results. Protect privacy by replacing direct identifiers with broader categories, while keeping enough information to support the audit. We import pandas to work with data more easily. Here, it helps create and manage small table summaries for reporting. We create a small sample dataset of patient appointment records for a clinical audit. Each record includes key appointment and patient details, such as identity, clinic, date, referral type, age, and follow-up status. This simulated data will be used to show how clinical information can be anonymized and summarized for reporting. First, convert the appointment records from a list of dictionaries into a pandas data frame. This makes the data easier to work with and prepares it for key analysis tasks, such as filtering, grouping, and summarizing. The code changes the appointment date column into a pandas date-time format. This makes it easier to work with dates, extract parts like the month, and summarize, group, or filter the data by time period. The code groups individual ages into broader age bands using the pandas cut function. It creates 3 categories: 0 to 39, 40 to 64, and 65 or older. This helps anonymize the data and makes analysis simpler by focusing on age groups instead of exact ages. The code converts each appointment date into a month and year period using pandas. This reduces detail from exact dates to monthly groupings, making the data easier to summarize and anonymize. The result is saved as a readable new appointment month column for later use. The code keeps only the data frame columns needed for audit reporting, such as age band, clinic, appointment month, referral type, and follow-up status. By creating a smaller dataset with just these fields, it supports focused analysis while reducing exposure of unnecessary personal information. The data is grouped by age band, referral type, and follow-up status to count how many records fall into each combination. Only combinations that actually appear in the data are included. The result is then turned back into a regular table with a count column showing the totals. This code protects privacy by suppressing very small counts in the summary table before the data is released. For each group, any count below 2 is replaced with the phrase less than 2, while all other counts are kept and converted to text. This reduces the risk of identifying individuals in small groups. The code displays a header explaining that the report is limited and anonymized. It tells viewers that direct identifiers have been removed and only the fields needed for the audit are shown. The code creates a compact summary table for teaching by selecting key columns on age bands, referral types, follow-up status, and reported counts. It then converts the result to a clean, readable string while leaving out the index. This keeps the output focused on the most important information and easy to present. The code prints a short message explaining that personal details such as names, birth dates, towns, and exact dates were left out of the report. This tells the user that the audit protects sensitive information and focuses on privacy. This script shows how to anonymize clinical appointment data for audit reporting. It removes direct identifiers, reduces dates to months, groups ages into broad bands, and keeps only key audit fields such as clinic, referral type, and follow-up status. The data is then summarized by counting follow-ups within each group, with very small counts masked to protect privacy. The result is a compact report that preserves useful patterns while excluding personal details and exact dates. In this lecture, you learn to format medical summaries into readable tables and narrative text using built-in string tools. Sort and filter records to highlight clinically relevant patterns or audit exceptions. And apply simple de-identification strategies to example datasets before reporting. In the next module, Module 5, we will go over none.
Thank you for your attention. See you all in the next lecture.